We are Group 71 and today we'll be representing the paper Lifelong Domain Adaptation via Consolidated Internal Distribution. Brief introduction as to what is the problem that we are trying to solve here. So this is some challenge in continual learning where deep neural networks, even though they can automate feature extraction, they struggle to generalize effectively in continual learning tasks. That is tasks where there is domain shift between training and testing data. So domain shift basically means when the input distribution of the testing and the training samples are different. Existing continual learning methods, they rely on fully labeled datasets, which are highly impractical due to high annual annotation costs. So UDA is an UDA enables knowledge transfer from annotated source data to an annotated target domain, but it requires simultaneous access for source and target datasets, which is very unsuitable for continual learning and is also prone to catastrophic forgetting. So let's see what is the problem statement. So we are given a classification problem in given labeled dataset D, where training samples are drawn from an unknown target distribution. While neural networks, they might optimize for this data, they will not generalize well due to the samples being drawn from a non-stationary input distribution. So we model this using sequentially ranked target domains with unlabeled datasets and varying input distributions over time. So to address domain shift and catastrophic forgetting, the network is composed into a encoder and a classifier network. Initial training on the source data makes the domains linearly separable in the latent space by updating the model at each time step such that the distribution between the internal distribution and the current distribution is not much. The model can generalize well across target domains, and however the current UDA methods, they rely on labeled datasets, and which is a very big constraint in continual learning. The core methodology of this solution involves consolidated internal distribution, which leverages an encoder to map the input source data into a latent space, where we learn a Gaussian mixture model in the embedding space, and we also generate pseudo-labeled datasets from the Gaussian mixture model, and assigning predictive labels using the classifier on the Gaussian mixture model. We also throw out the samples with a very low confidence, and to prevent forgetting, we use experience replays, which help us to mitigate catastrophic forgetting, where we store representatives of each class using cluster means like in a memory buffer, or using strategy like mean of features. This helps us to identify the most representative samples of that class. So the final LDA UCID algorithm, it integrates CID and experience replay to enable effective domain alignment and knowledge retention across tasks. Mathematics behind this algorithm. So upon learning the initial source domain, the encoder is learned to take the source data and transform it to the latent space, and the classifier takes the input from the latent space and takes it to the target space. Then we draw samples from the Gaussian mixture model to build our pseudo labeled data sets, where the labeled data determined from the model predictions. We also do the MLE estimation for the Gaussian mixture model using our labeled data set. Then after we have gotten our pseudo labeled data set, we use the SWD metric and minimize the loss function to using the pseudo labeled data sets to find the new values of the parameters. We have seen so far will help us to mitigate knowledge transfer across various domains, but this will not help us in catastrophic forgetting. So to get rid of catastrophic forgetting, we pick n by k samples per class, which are closest to the cluster means in the latent space, and then we use we use these as representations of the class, and then we minimize this loss quantity, and we integrate using that into our pseudo labeled dataset and minimize this loss quantity, which will help us in preventing catastrophic forgetting. So this is the LDA UCID algorithm in its completeness. So first we estimate the parameters of the neural network by using backpropagation on the labeled dataset. Then we find the parameters of the Gaussian mixture model by doing MLE estimate on that. Then we initialize our memory buffer by picking the means that are nb by k points per class that are closest to the mean in the latent space of that class, as they are the best representatives. Then for each target distribution, we generate a pseudo data set from the GMM, and then use prediction from the classifier network and throw with the samples with very low confidence. And then for t is equal to 1 to for all of the epochs, we draw batches from these data sets. Then we update this model by solving the minimization problem. Then we update our probability distribution, and then we update our memory buffer to intersection of both of these, and then we go back to step 7. results achieved by the testing of this algorithm. So we used it on datasets such as MNIST, USPS, SVHN, and its ImageCLF, Office Form, and Office Caltech. It had significant accuracy improves on target domain and very nice retention on prior task knowledge. It was effective on balanced dataset and lagged slightly in large domain gaps. It was competitive with state-of-the-art UDA methods and outperformed many despite lifelong constraints. And we see that in ablation studies, large memory buffer helps to improve retention and domain alignment, why SWD is very critical. So the LDA UCID algorithm successfully balances generalization and forgetting in lifelong UDA.